optimization of basic blocks. Here, these are the types of optimization of basic blocks. First one is that the DAG representation of basic block, then finding the local common sub-expressions, and dead code elimination, use of algebraic identities, and representation of array references, and pointer assignments and procedure calls, and resembling basic blocks from DAG. From DAG. Okay, these are the 7 points under this optimization of basic block. How to optimize that basic blocks, right? So basic block means that is the flow graph diagrams. Okay, so in that flow graph diagram, each and every node is at one block. Okay, so how to optimize that basic block? So using these 5 techniques, we can optimize the basic blocks here. So one by one, here the DAG representation of basic blocks. The many important techniques for local optimization. Many important technique for local optimization. So begin by transforming a basic block into a DAG. Basic block into a DAG. DAG means directed acyclic block. So whatever that basic blocks are there, so that how to identify that basic blocks, we have that algorithm. With that algorithm, we can identify that basic blocks. Okay, and then we can connect that basic block. Then it forms a flow graph. It forms a flow graph. So here, by transforming a basic block into DAG, so that is whatever that important technique we are using for local optimization. Okay, so we introduced the DAG as a representation for single expression, and the idea extends naturally to the collection of expressions that are created within one basic block. And we construct a DAG for basic block as, so we have to construct a DAG for the basic block. So how you are going to construct that, already you knows that. So there is a node in the DAG for each of the initial values of the variables appearing in the basic block. Okay, so whatever the nodes are there for initial values, and that variables are appearing in the basic block. The first expressions are there, no, whatever that initial values of the variables are there, that declaration form, and there is a node n associated with each statement s within the block, and the children of n are those nodes corresponding to statements that are the last definitions and prior to s of the operands used by s. Okay, and the next node n labeled by the operator applied at s and also attached to n is the list of variables for which it is the last definitions within the block. Okay, so here it is labeled by the operator applied. Operator means it is that uh, it is a sub node, yeah, interior node. Okay, it is interior node, and also attach it to en. We can attach to that whatever that the next sequence list of variables, and for which it is the last definition within the block. And certain nodes are designated output nodes. These are the nodes whose variables are live on exit from the block. That is, their values may be used later in another block of the flow graph. So calculation of these live variables is a matter for global flow analysis. Yes. Here, if you want to declare that global flow analysis, then here whatever the variables we have declared in that declaration section, either it is a local declaration or global declaration, that variable you have to use the later cases. Okay, so otherwise it is not a live, it is a dead code. Okay, the live variables means compulsory we have to use whatever we have declared in the declaration section, either it is the local declaration or the global declaration. So whatever you have declared that variable, if you are using later, then we can say that it is called live variable. Otherwise, it is called a dead code. Okay. Here, the DAG representation of basic blocks. Let us perform the several code improving transformation. So why we are using this DAG representation, the basic block? So for performing that code improving transformation, and the code represented by the block. So only that our aim is to improve the codes, code improving transformation. We can eliminate local common sub expressions, that is instruction that compute the value that has already been completed, that has already been computed. Okay, we can eliminate dead code, that is instructions that compute a value that is never used, that is never used. Okay, so here we can eliminate dead code if it is not using that variable. You are declared somewhere, and if you are not using at all, then what is the use of it? No use of it. Okay, then we can say that it is a dead code. The instruction that compute a value and that is never used, that is never using. So we can reorder the statements that do not depend on one another, right? Do not depend on one another. Such reordering may reduce the time. Such reordering may reduce the time a temporary value needs to be preserved in a register. In a register, and here we can apply that algebraic laws to reorder the operands of three address instructions, and sometimes thereby simply the simplify the computation. So we can apply that algebraic laws, whatever the algebraic laws are there, for reorder that operands of the three address instructions, and sometimes thereby simplify the computations also. Okay, so like that we can eliminate that local common sub expressions in that. So that is called DAG representation of basic blocks. Next, finding local common sub-expressions. Local common sub-expression. So whatever that common sub-expressions are there, so that common sub-expressions we have to eliminate it. We have to eliminate it. Here, common sub-expression can be detected by noticing as a new node M. Okay, new node M is about to be added, whether there is a existing node N with the same children, with the same children in the same order and with the same operator. Okay, so whether there is a existing node N with the same children and in the same order and with the same operator. If so, if so, then we can compute the value. We can compute the value. You can compute the value as m and may be used in its place. In its place, and this technique was introduced as the value number. It's called value number method of detecting common sub-expression. Common sub-expression. Here, the DAG for the block. The DAG for the block. Here, this is the DAG. This is the DAG for these statements. For these statements here. So, what are that statements? A equal to B plus C, B equal to A minus D, and C equal to B plus C, and D equal to A minus D here. D equal to A minus D. So, this is the expression, and for this expression, here this is the DAG representation for that expression. So, how to draw that? Here A equal to B plus C. Here define B and C, and B plus C. It is B plus C. So, it is called A. So, this one is A. Okay, and B equal to A minus D. Here A is already defined, already there. A is here, this one, and D is not there. So D we need to define here. So this is A, this is D. Then here minus symbol, minus. So A minus D is, it is B. It is B here. C. C equal to B plus C here. Here B is already there, B is already there, and C is also there here. So B is defined, C is also defined. So just here plus node, and we can connect from B to plus and plus to C. Then it is B plus C here, B plus C here. And next, D equal to A minus D here. B is also A minus D, and D is also A minus D, A minus D. Okay, here, so where is B? Here this is B. B is that A minus D, A minus D. So here B comma D, we can put it here. We can put it here, right? And see here, here, here this one is, this one is, this one is B equal to A minus D and D equal to A minus D. So here it is, we have drawn this one, and here B plus C, A equal to B plus C and C equal to B plus C here. So here its value is changed here B. So we can draw this and we can connect it. We can connect it. Here we can construct the node for the third statement C equal to B plus C. And we know that use of B in B plus C. Use of B in B plus C. Yes, use of B in B plus C. Refer to the node label. And because that is the most recent definition of B. Thus, we do not confuse the value computed at statement 1 and statement 3. So, however, the node corresponding to the fourth statement, D equal to A minus D, has the operator minus, has the operator minus, and the node with the attached variable A and do as children, do as children here. And since the operator and the children are the same as those for the node corresponding to the statement 2, and we do not create this node, do not create this node, but add D to the list of definitions for the node labeled here. Okay, so this is called finding local common sub-expressions. Whatever the common sub-expressions are there, that common sub-expressions we can eliminate it. So when we look for common sub-expressions, so we really are looking for expressions that are guaranteed to compute the same value, compute the same value, and no matter how that value is computed, as the DAG method will miss the fact that the expression computed by the first and fourth statement in the sequence. The DAG method will miss the fact and the expression computed by the fourth and first and fourth statement in the sequence. Okay. Here A equal to B plus C, B equal to B minus D, and C equal to C plus D. Here E equal to B plus C is the same, is the same. That is, even so that B and C both change between the first and last statement, their sum remains the same. Their sum remains the same here. So because B plus C equal to either it is B minus D or C plus D, then the DAG for this sequence is but does not exhibit any common sub-expression. However, the algebraic identifiers applied to DAG may expose the equivalence, expose that equivalence here. Here, B plus C, B plus C is A, and B minus D is that it is B, and C plus D, this is C plus D. Okay, so this is called C. Then after that, E equal to B plus C. So here B is there and C is there. So then we can draw that one more interior node and we can connect it, right? But the DAG does not exhibit any common subexpressions. However, algebraic identities applied to the DAG and may expose that the equivalence here. Yeah, right. This is the example for that finding local common subexpression. Next, dead code elimination. So, what is that dead code elimination? Is there any code it is written by the programmer or specialist and must be used? That code must be used in the program. Okay. So, in the latter sections, we can use that statement. Otherwise, that statement is a dead code. The operation on DAG that correspond to dead code elimination can be implemented as follows. So we delete from a DAG any root node with no ancestors. Here that can be implemented as follows. The delete from a DAG any root and node with no ancestors and that has no live variables attached. That has no live variables attached. Repeated applications of this transformation will remove all nodes from the DAG that correspond to dead code here. Okay. Next, here in figure A and B are live, but C and E are not live. Here, where is that A and B, and we can immediately remove that remove root label E here. Okay, here AB is there. AB, this is A and this is B here. This is B here. But C and E, C and E, here the C and E are not live here. Here it is not live because these two are we are utilizing in the next section. So the node labeled C becomes a root. C becomes a root and can be removed. The root labeled A and B remains since they each have live variables attached. Live variables attached here. Okay. So the use of algebraic identities. Next is that fourth one, use of algebraic identities. Algebraic identities represent another important class of optimization on basic blocks. For example, we may apply the arithmetic identities such as here x plus 0, 0 plus x equal to x, x minus 0 equal to x. Here x into 1, 1 into x equal to x, z by 1 equal to z only. So to eliminate the computations from basic blocks. So these kind of computations are there, no? These kind of computations we can eliminate from the block. So because even if you perform that, you are going to get that the same here. No need to perform it. No need to perform it here. So we can eliminate that computation from basic block. Another class of algebraic optimization and includes local reduction in strength, that is replacing more expensive operator by a cheaper one as in. So how it is, x square is equal to x into x, 2 into x, 2 into x means it is 2x, 2x means it is x plus x we can write, x plus x we can write. If it is 3x, then x plus x we can write, x by 2. So it is x into 0.5, x into 0.5 we can write. And a third class of related computation is constant folding. Is constant folding. So here we evaluate constant expressions at compile time and replace the constant expressions by the values. Thus expressions 2 into 3, 2 into 3, sorry, 2 into this 3.14 would be replaced by 6.28. 6.28. Okay. Many constant expressions arise because after this one, after performing, we can replace it. What you are going to get that 6.28. So directly we can replace it. And many constant expressions arise in practice because of the frequent use of symbolic constants in program. In program. So these are all some identities are there. These identities we can remove it, and these are the some these are the sum operators, and which is equivalent to that sum operator. So whatever the operands are appeared in that, so that operators we can replace it. We can replace it with the cheaper operator. Okay, from a more expensive operator by a cheaper one as. So we may apply that arithmetic operators as. Okay. By evaluating all these things, nothing we are going to get here. So that's why we no need to write these kind of expressions in the program. So directly we can remove or eliminate this from the program, right? Next, fifth one. So representation of an array references. Representation of array references. So how to represent that array references? Array references. Okay. So here, at first glance, it might appear that array indexing instructions can be treated like any other operators, and consider for instance sequence of three address statements x equal to a of I, x equal to a of I, and a of j equal to this y, a of j equal to this y, and z equal to a of I. So if you think that a of I as an operation involving that a and I similar to a plus I, then it might appear as if the two uses of a, I, and were common sub-expressions. In that case, we might be tempted to optimize by replacing the third instruction z is equal to a of I by the simpler z equal to x. However, since j could equal I, the middle statements may in fact change the value of a of I. Thus, it is not legal to make this change. The proper way to represent the array access in DAG as here assignment statement for an array is like x equal to a of I. This is an array statement. This is an array statement. Then how we are going to represent it by creating a node with operator this one, operator equal to this one, and two childrens representing that initial value of array a0. In this case, the index is I, and the variable x becomes the label of this new node, label of this new node. So this is the node, and this I is that x becomes the label of this node. So this is label of this. So one minute. And assignment to array like a of j equal to y, a of j equal to y, which is represented by a new node with an operator, here this one, and three children representing that a0, j, and y, j and y. Here is that two childrens here. Here is that two childrens. Okay, that is representing initial value of array a0 in this case, and index I here. Index I here. But here it is that three childrens here. Is that three children? That is a0, j, and y. and there is no variable labeling this node. Labeling this node. What the difference is that the creation of this node kills all currently constructed nodes whose value depends on A0. And a node that has been killed cannot receive any more labels, that is, it cannot become a sub expression. Common sub expression. Okay. So this is the fifth one, representation of array reference. If x equal to a of I, then how to create that? Or a of j equal to y. The DAG for the basic block here, the DAG for the basic block. Here x equal to a of I, a of j equal to y, and z equal to a of I shown below. Here, figure the node n for x is created first. Node n for x is created first. Okay, x is created first, but when the node labeled this is created n is killed. Here it is a of node. This one is that x node a of I, x equal to a of I. It is a of I. It is two children for this node and it is labeled x. Okay. Next, when the node z is created, it cannot be identified with n, and a is a new node with the same operands a0 and I0. So here, in case of this one, it is a of j equal to y, a of j equal to y. Okay, so it is a of j, equal to y. So it is a is already there, and it is j, and it is y equal to y. It is three children. Here is only two children, a and I. Here is in case of a of j equal to y, it is three children. Okay, a z0 and y0. And next z equal to a of I. Z equal to a of I. So it is z equal to a of I means it is this one z, and a is this one, I is this one, right? So this is the DAG for sequence for array assignments. How you are going to draw that array for array assignments, here, right? And next pointer assignments and procedure calls here. Here, when we assign indirectly through a pointer, as in the assignments, so now here is the pointer declaration. X equal to star pointer and star q equal to y. So it is pointer type variables. Star means it is pointer type variable. So we do not know what p or q2. In effect, x equal to star p is a use of every variable, whatsoever, and star q equal to y is a possible assignment to every variable, As a consequence, here the operator star must take all nodes that are currently associated with identifiers as arguments, which is relevant for dead code elimination also. It is relevant for dead code elimination. More importantly, the star equal to operator kills all other nodes so far constructed in the DAG. Okay. Here the operator must take all the nodes that are currently associated with the identifiers as arguments. It is relevant for dead code elimination. Here, there are global pointer analyses one could perform that might limit that set of variables a pointer could reference at a given place in the code. Even local analysis could restrict the scope of a pointer. For instance, in the sequence p equal to ampersand x and star p equal to y. We know that x and no other variable is given the value of y is given the value of y. So we don't need to kill any node, but the node to which x was attached. Here, procedure calls behave much like assignments through pointers. In the absence of global data flow information, and we must assume that procedure uses and changes any data to which it has access. Thus, if variable x is in the scope of the procedure p and a call to p both uses and the node with attached variable x kills that node. Kills that node. Yeah, this is in case of these pointer assignments and procedure calls. Next, reassembling that basic blocks from DAG. So reassembling that basic blocks from DAG. So after we perform whatever optimization are possible while constructing the DAG, or by manipulating the DAG once constructed, so we may reconstruct. Reassembling means we can reconstruct the three address code for basic block for which we built the DAG. For each node that has one or more attached variables, and we construct a three address statements that computes the value of those variables, one of those variables. Okay, and we prefer to compute the result into a variables that is live on exit from the block. Exit from the block. Here we prefer to compute the result into a variable that is live on exit from the block. If we do not have a global live variable information to work from, we need to assume that every variable of the program is live on the exit from the block, but not temporaries that is generated by the compiler to process the expression. So it is not that temporaries, only that whatever the variables are there, variables we have declared, so that is live. If the node has more than one live variable attached, okay, then we have to introduce a copy statement to give the correct value to each of those variables. Sometimes global optimization can eliminate those copies. Sometimes global optimization can eliminate those copies if we can arrange to use one of the two variables in place of the other. If we can arrange to use one of two variables in place of others. Okay, so this is called reconstruct the basic blocks. Okay, how to reconstruct it? For example, here the same same sentences, same statements we are using. Three statements here. Here we decided that if B is not live on exit from the block, then the three statements. Here A equal to B plus C and D equal to A minus D and C equal to D plus C. So suffice to that reconstruct the basic block. Third instruction C equal to D plus C must use D as an operand rather than B. Because the optimized block never computes B. Optimized block never computes that B. If both B and D are live on exit, or if you are not sure when whether or not they are live on exit, then we need to compute b as well as d. We can do that. So the sequence a equal to b plus c and d equal to a minus d, b equal to d here, b equal to d here. Yes. Then c equal to d plus c, c equal to d plus c. This basic block is still more efficient than the original, although the number of instructions is the same, but we have replaced a subtraction by a copy, and which tends to less expensive on that most machines. Further, it may be that by doing the global analysis, we can eliminate the use of these computations of B outside the block by replacing it by uses of D. In that case, we can more back to this basic block and eliminate B equal to D later. We can eliminate this copy if whenever that this value of B is used and D is still holding the same value. This situation may or may not be true depending on that how the program is recomputes D. Okay, so we can reconstruct it. Here, please note down these optimization of basic blocks. So these are the seven types, seven techniques for optimizing that basic blocks. Yes, please note down this. All of you note down. Hmm? లేదుగా. Next slide. is completed. Hello, completed it. Raviteja, yes. D5.